Cool. Okay, hi everyone. Marhaba. I'm Andrew. As Maria said, I'm a research engineer at DeepMind. And I'm going to talk about the application side of diffusion today. I'm still hoping for this part of the talk to be a bit technical, so bear with some of the formulas, but they're all going to come with nice diagrams. So hopefully it's not too hard to follow. I'm going to talk about three things today, three applications: image diffusion, video diffusion, and then finally diffusion for weather. Which might sound a bit random, but spoiler alert, I'm a bit biased. I work on the weather team at DeepMind, and we use diffusion to forecast the weather. And soon you'll see that actually weather forecasting is not so dissimilar from the other two applications, which I'm going to talk about briefly first. Okay, awesome. So there's a lot we could talk about when it comes to image and video diffusion. And actually, Safa already touched upon one of the seminal papers in this field, which was the DDPM paper. So I'm not going to recover what she just spoke about. There's just two things I'm going to point out, because I'm going to contrast them later on when I speak about weather forecasting. So I'd like to show you how things look a bit different when we move over to a domain like weather versus when we're in a domain like image and video. And then for video, I'm going to use a seminal paper by the same main author on video diffusion models. And I'll talk about how we take an idea like image diffusion and apply a simple extension to get to video. And really my aim is to just drive home how simple ideas work and how something that seems like a bit of an abstract research idea can be applied to an actual domain. Cool. So the first thing I want to point out about the DDPM paper is the architecture that they use. And actually, for those of you that were here on Monday, Sahra already spoke about this architecture. It's called the UNet architecture. And usually the way it works is we send in tensors that represent an image. So we have, our height dimension, our width dimension, and channels that represent the colors, say. And the objective of the UNet is to do some downscaling and upscaling to really extract the features that are in this image. So this is an example of using a UNet to segment an image of a brain scan. And for those of you that do medical imaging here, sorry, you probably know more about this than I do. But the idea is that we've taken a network that we know is good at dealing with images. And so it's like a bit of a learning point here, that it's, when you come to applying an idea in a new domain, don't reinvent the wheel. We knew it was good for segmentation, so we've applied it to generate images. But the second thing is to not be afraid to update. And what I mean by that is you'll see that more modern implementations of the UNet, amongst other things that they've changed in it, add this sort of self-attention in the convolution blocks, which we learned about earlier in the tutorials and talks on Monday. And I'm bringing this up because you'll see in a moment that this attention mechanism is important for when we move to the video domain. Okay, and the second thing I want to speak about to sort of round off the DDPM paper is how exactly we then evaluate this diffusion model that we've just trained to denoise. And in particular, I want to point out that sort of the name of the game when it comes to image diffusion is realism and diversity. It's how realistic are my images and how diverse are the images that my model can produce. And you'll see later on in the talk, keep that in mind, that that's not really the case with weather. We care about different things there. So the idea with evaluating our image and video diffusion models is to use what we call a pre-trained discriminator. It's let's get something to critique how good my generator was at making images. And usually the canonical sort of setup for this is to use a network called Inception v3 and to train it on an ImageNet data set, which is a data set filled with images, and specifically to train it on the task of classifying these images. So, we'd hope that the pre-trained ImageNet v3 can take something like a photo of a dog and tell me with high confidence that it's indeed a dog. And I'm just going to point out that the sort of final two output layers of ImageNet are the following. We have sort of this output 2048 feature vector, which is what we like to say represents these high-level features of the images, some patterns that it's learned about images. And then the final 1,000 outputs are the classes. And these will be important in just a moment. Okay, so the simplest evaluation metric that people like to use for images is called the inception score. And the idea of the inception score is really, we just want to evaluate how well our generator has done at making images. And specifically, the two things we want to evaluate are the entropy and the diversity. So what do I mean by this? Let's look at two examples. In the case where my model is generating an image, I want to be sure that it's generated a good quality image. And what this means is that I expect ImageNet v3 to be able to confidently classify what the image actually is. So in this case, a photo of a dog, I'm expecting ImageNet v3 to know it's a dog. If it doesn't, I've probably done a bad job. And also for diversity, I want to make sure that my model isn't just good at making images of dogs. If that was the case, okay, great, I've got a useful dog model, but otherwise it can't do anything else. So that's pretty useless. And so really all the inception score does, bit of a complicated formula, it basically just seeks to maximize how different, it aims to measure how different these two distributions are. I want to have a diversity across all my images as much as possible, and a sharpness across my actual single image generation as much as possible. And so the higher the inception score, the better. And we're making use of these classes that the model is outputting, which I think might make you realize that this is a bit of a flawed way to evaluate a generative model, for two reasons. The first is that it's really reliant on what Inception v3 has learned. If Inception v3 never learned what a photo of a dog looked like, that's not my problem. My network is still good at making photos of dogs. I shouldn't suffer because of that. And the second thing is, there's kind of a bit of a way to hack this, right? Which is that I could have good inter-class diversity if my model was really good at making a photo of one dog and one cat and one shark. It would get a good diversity score, but it doesn't mean that it's capable of generating diverse dog images or cat images. So it's a pretty easy way to hack the score. So we don't really use that metric much anymore these days. More recently, you might see something called the Frechet inception distance, or FID. And the idea there is, instead of just evaluating the generated images, I want to compare how well the generated images look to a real set of images. So what I'm going to do is I'm going to pass a real set of images through Inception v3. I'm then going to pass a generated set of images through Inception v3. And I'm going to stop one layer before. I'm not going to look at the output classes and rely on Inception v3. Instead, I'm going to look at the high-level features that it learned about these images. I'll make an assumption that these are Gaussian distributions, compute the mean and the covariance matrices, and then from that I can compute this Frechet distance between the two distributions. And ideally, the distance is as small as possible, because that means my generated images look realistic. And so you'll see this sort of Frechet inception distance pop up quite a lot. Okay, awesome. And I think this is a really nice slide to visualize how the Frechet inception distance gets worse the more you distort images by adding some noise, blurring, obfuscations, and distortions. Cool. Okay, and the last thing I want to talk about in this section before I get on to my love of weather is how we go from image to video. And I'm going to talk about the simplest idea. This is what they use in the video diffusion paper. Really, the idea is, let's just take our existing tensors that represent these images, and let's think for a moment what a video actually is. Really, if you look at this sort of cute animation at the bottom, a video is nothing more than a sequence of images with some temporal consistency across them. So what we do with these video diffusion models is we add an extra frame dimension. So what this sort of diagram is representing is, this orange cuboid is one frame, and then the blue cuboid is another, and I'm adding a new extra frame dimension. And now, as I mentioned before, we have this spatial self-attention in our conv blocks. Well, we're going to add a temporal attention across the actual frames. And this is how we get the model to pick up on the temporal relationships between the frames that are in my video, so that I end up with something like this, where there's a consistency between every single image that's in the video. Awesome. And then some of you might be thinking at this point, well, hang on a second, how do I train this to make arbitrary video lengths? And again, you might remember from the great tutorial on Monday that it's really ideal to have your batch that you train on to all be of the same dimension. So instead what we do, and what they do in this video diffusion paper, is they only ever train on 16 frames at a time, and then they use a technique called inpainting to auto-aggressively roll out to longer videos. So what this looks like is a bit like the following. Hello? Nice. So what this looks like is the following. I'll generate my first 16 frames, and then sort of conditioned on the first part, I'll make my next 16 frames, and so on and so on. And that's how I get these nice, longer videos. Cool. And then for the metric, we're just going to move from the Frechet inception distance to the Frechet video distance, which is really the same idea, except I'm not just going to use Inception v3, which has only learned about images. I'm going to use something called an i3D network, which also has been trained on video. So it really captures these temporal and spatial distributions between real and generated videos. And that's how I'll compare. Sure. I think in this case, it was just like an empirical choice that they used to maximize the efficiency of training the model. So yeah, I should be specific. This 16 is not used across all papers. It's specifically in the video diffusion paper that I'm mentioning. And then I think in the paper, they only ever do longer autoregressive rollouts to 64 frames. But so it's a demonstration that this works. Nice. Okay, so I'm now going to bring up these animations from the first slide. And I want you guys to take a moment to realize that actually, this video of a forecast of humidity that I'm showing you on the right over the Earth is not so dissimilar from the video of this cute animation that's in the middle. And really, at the end of the day, we lent on this for a lot of motivation and inspiration in weather forecasting, where the idea, the name of the game, is to just treat a weather forecast as though it was a video. We're just going to treat each frame of the weather as a point in time, and then we want to train a model that's able to roll out each of the frames in time and give me my weather forecast up to 15 days into the future. Cool. So let's dive into that. And let me clarify a few things. So I'm going to do a bit of a background explanation of what I mean by weather forecasting, just so we're all on the same page. And then I'll dive into the actual diffusion specifics of the model. So when I say weather, I'm specifically talking about the task of medium-range global weather forecasting. And if that's not any clearer, then let's dive into that. So what is medium-range global weather forecasting? The aim is to predict the state of the atmosphere. So that's this sort of 3D space that exists around the Earth, all the way sort of in elevation, up to 15 days into the future, everywhere on Earth for multiple variables. So the medium range is the 15 days, and then the everywhere on Earth is the global weather forecasting. And these are some examples of variables which our models predict. So you've got wind, temperature, and humidity all the way on the right. And recently, we've really seen an explosion of people trying to use machine learning in order to learn this task. And this is for a number of reasons. There's a lot of data available, but the size of this data is large. So it's only really been very recently that we've had accelerators and algorithms that are able to deal with the scale that is required to do weather forecasting. And what do I specifically mean by the state of the atmosphere? Just to give you a flavor for what this data actually looks like. We usually train these models on data sets called reanalysis. And the idea is I'm going to collect all of these weather measurements that I have, from satellites, weather stations, any thermometer that lies around, and I assimilate them into a nice gridded homogeneous state that represents the Earth. And the way I do this is with an inverse problem. I say, okay, what state do I need to have had to have given me all these measurements that we made with our satellites and rain gauges? And what's nice is that what pops out of this is a super homogeneous, sorry, you can see I drew the lines on top of this, a very nice and gridded state which looks a lot like a tensor, and so is really amenable to machine learning. We can just feed it into our model and train the model on. Okay, and then one more step back. Before I dive into GenCast, I want to talk about what our UNet was. Again, this idea of not reinventing the wheel. So 3 years ago, before I joined DeepMind, my team published a paper on GraphCast, which was their first weather forecasting model. And sort of the one-line summary of what GraphCast is a learned simulator that's based on graph neural networks. For those of you that aren't familiar with graph neural networks, I unfortunately won't have time to dive into them today, but the idea is that they're a type of neural network that learns relationships between entities. And in essence, the way GraphCast works is we're just going to use the network to take the current state of the weather and step us one frame into the future. So take us from one frame of the video to the next frame of the video. And it does this in 3 stages. We have an encoder. This is one GNN that learns to map from this gridded data that I just showed you onto a nice mesh that we use to represent the Earth. So we have a sort of internal latent mesh, which is a sphere that represents our Earth. We have another GNN on this mesh called the processor, and this is the GNN that's actually learning the relationships between elements on the Earth and how the weather interacts between them. And then we have a final GNN called a decoder, which takes us back from our latent mesh to the gridded state that I just showed you earlier. And so one application of this takes me from now to 6 hours into the future in GraphCast's case. And the way I'm going to get this full video of the weather forecast all the way out into the future is I'm just going to apply GraphCast autoregressively. So I take the output of what GraphCast predicted and feed that back in as an input. And then that gives me the next step, and the next step, and the next step. And all of a sudden, I've done my whole forecast. And this is how GraphCast is trained. Let's ignore all of these for a moment. Like, sort of with any machine learning model, I'm going to impose some objective function. Really, the only thing I want to point out to you about GraphCast is that it's trained with a deterministic mean squared error loss. I'm basically saying to GraphCast, hey, give me your best guess of what you think the weather is going to be like at some point in the future, and I'm going to tell you how well you did at it. And again, the key word here is deterministic. And before I tell you why a deterministic model sucks, I think it would be unfair to my colleagues to not first tell you about how amazing this model was, before I bash it. It really did well for its time. It was fantastic at predicting hurricanes. Here's an example of a hurricane, which GraphCast is the blue forecast. The black line is where it actually went. And then the red line was the SOTA, or used to be the SOTA at the time, which GraphCast beat. And I think there was a lot of positive reaction to this model, and rightly so. It really was a step change in moving from traditional weather forecasting techniques to using machine learning. But as I said, it was deterministic. And the problem with a deterministic weather forecast is you just get the model's best guess. There's no sense of uncertainty. There's no probabilities. I'm probably going to miss extreme events that are unlikely to happen because the model's going to play it safe, and it wants to make its best guess of what's going to happen. And this isn't really useful for something like weather, where we really want to get these tail ends of the distribution right. So instead, we move over to what we call probabilistic ensembles. And this is where GenCast comes in. The idea is, let me get a model that can give me multiple possible future events that can occur. So, I'm at my current state in time. I'll do one forwards trajectory. Okay, that's a possible reality. Another one, another one, another one. And from this, I can get an ensemble of possible weather forecasts, possible future trajectories, and I can use that to estimate uncertainties, probabilities, and expectations of weather events happening. And now I've solved this issue of just getting a best guess. I've now got a nice ensemble of guesses. Okay, so let's talk about GenCast and diffusion. So the name of the game here is, exactly like Safa explained, we're trying to learn some distribution conditioned on some input. And in Safa's case, this was image generation. So the thing we were trying to learn or generate were images, and what we were conditioning on was text. Something like, give me a photo of a cute dog, and we denoise from Gaussian noise, hopefully what you think is a cute dog. In the case of weather, it's super similar, except the idea here, the thing that I want to generate is a future weather state, and the thing that I want to condition on is the current weather. And so we call this many images to many images diffusion. And the reason that there's the word many there is you have to remember that I'm predicting multiple variables. So if you will, imagine that this image actually has some sort of stacked frames to it where there's a bunch of variables that I'm predicting in time. And you can see that I denoise from Gaussian noise to a sample of the future weather. And different initializations of the noise are going to give me different future weather states, just like Safa explained for images. Okay, so let's sort of dig down and make this a bit more rigorous. The idea is that given the current state of the weather, I want to predict the weather all the way up to some point t in the future. And the first thing I'm going to do is I'm going to factorize this distribution. So I'm actually going to break it down and make an assumption that weather is a Markov system. For those of you that aren't familiar with Markovian systems, don't worry. Really the key element of this that I care about is that a Markov system is memoryless. So what this tells me is that actually my ability to predict any point in time only needs the information from the previous step. So I don't need to know in 7 days what was happening now. If I'm predicting in 6-hour blocks, in 7 days I just need to know what happened 6 hours before that. And then actually we're going to relax that a little bit more. I'm going to make what we call a second order Markov assumption. And I'm going to assume that knowing the state of the weather at any point in time, I just need 2 previous frames. So 6 hours and then the 6 hours before that. And this is what GenCast is. GenCast is a diffusion model that learns to, conditioned on 2 previous weather states, give me the next weather state. And you'll see in the slides to come that I'm going to highlight a bunch of things in green. And anything I highlight in green is something related to weather. It's where we've taken the fact that we have this general diffusion paradigm, but we're going to adapt it to the domain that we're working in. And the reason I want to highlight this is I just want to give you a flavor of what it looks like to take, again, a sort of abstract research idea, come to a domain, and think carefully about what it means to apply that research idea to the domain. And so this Markov and second order Markov assumptions are assumptions that are made a lot in the weather community. Okay, so what's the setup? So Safa explained that the sort of usual setup is we have a network that we're trying to train, and I'm going to refer to it as the denoiser. As you might guess, it's learning to remove noise. And we have some sort of noisy input and some sort of output. So to link this back to what we spoke about in DDPM with Safa, the noisy input was the sort of image that I'd noised, and the output was I was just asking the network to predict what noise had been added. And this is how I computed the loss. The setup is a bit different in GenCast, so let's break each of these down. Okay, first of all, I'm going to talk about the output. So in GenCast's case, we don't actually ask it to predict the noise. We're going to ask it to predict sort of the unnoised version of its input, which is kind of the same thing. Except I'm going to be a bit specific about what it is we're asking it to predict. We call it a normalized residual. And if that sounds complicated, let's break it down. The idea is, instead of asking GenCast, hey, I've got the current 2 frames of the weather, give me the next one, I'm going to ask it, give me what I need to add to the current weather to get the next one. So sort of as an image, I've got my current state of the weather. I say to GenCast, hey, give me the output. I'm going to take that output, scale it up. This is the normalized part. And then I'm going to add it on to the current weather. And this is the residual part. And this is how I'm going to get my next weather frame. And why do we do this? Well, 2 reasons. So the normalization part, this isn't really specific to weather, but it's generally a trick that we use in machine learning. The idea is you don't want your model to focus on things that are larger than others just because they're larger. Let's put all of these variables on the same scale. So we normalize them to be a 0-1 Gaussian, effectively. And then for our residuals, well, weather is a dynamic process. The whole point of this is that it's a sort of system that's moving forwards in time. I want the model to focus on that. I want it to learn how things change, not learn how to reconstruct a weather state, right? And so that's why we get these normalized residuals out of GenCast, not the direct next weather state. Okay, and then what do we take as input? So Safa explained one way of how we condition models, which is to add them sort of as an embedding inside the deep layers. But there's actually a simpler way, which we found worked well enough for GenCast, so we stuck to it. And that's to just provide the things you want to condition on as an additional input to the model. So actually, what GenCast takes as input is these 2 previous states of the weather that we want to condition on, and then the noisy residual that I want it to predict. So this sort of noisy part is exactly the same as in Safa's setup. I want it to predict something, I'm going to give it the noisy version of something. But one key distinction is where exactly this noise comes from. So I've got my residual that I want the network to predict. The noise I'm going to add to it is what we call isotropic white noise. And this is just a fancy word for noise on a sphere that's rotationally invariant. So what we would consider is truly IID. And the reason for that is that we live on a sphere, and the weather is a system acting on a sphere. So we want to model that correctly. We don't want the Gaussian noise to be on a grid like we did in the case of image diffusion. We want it to be on a sphere. So we'll sample it there and then project it down to the grid so that it's correctly represented. Awesome, and then let's talk about the final part. What's the actual architecture? So remember, I pointed you guys out to GraphCast, and I called it our UNet. And that's exactly the case. We pretty much took GraphCast as it is, and we made only one change to it. And the change we made really was more of like a memory optimization change, a computational efficiency change, as opposed to trying to reinvent the wheel. We took the encoder, processor, and decoder. We just swapped out this middle GNN for a sparse transformer. And so now what we do is, again, as many of us learned on Monday, we do this attention across the nodes that live on this mesh. And the way this works is we sort of define what we call a k-hop neighborhood. So in the case of GenCast, we have a 32 k-hop neighborhood. Again, sounds complicated. It's very actually simple. I'm going to take every single node. Every node that's connected to it is a 1-hop. Every node that's connected to every node it's connected to is a 2-hop, so 1, 2. And I repeat that 32 times. And then I get this sort of nice blue region, and that's where I'm going to do my attention over. And interestingly, this is a local attention, right? I'm not doing this attention over the whole planet. And this is, again, a domain assumption we can use. In reality, weather is a local phenomenon. I don't really care what's happening right now in Brazil if I'm trying to predict the weather in Qatar. I just care about what's happening in the region. I'll let future steps of this model roll out, transport this information across from Brazil to Qatar, but right now I just care about this local phenomenon that's occurring around me. Okay, so now we've defined the sort of 3 elements of our setup. What's the actual task? How do we train this model? Well, as you might expect, sort of just to be clear, YT is the output of our model, d theta is the denoiser, and these are the inputs, nothing more than that. I'm going to train it on a mean squared error loss, just like they did in DDPM, for the outputs of this model versus the actual ground truth residuals that I wanted it to predict. And this time, sorry, I'm not going to cut you some slack. I'm actually going to go through what these terms are in the loss because I want to give you the final flavor of how we adapted to the domain when we trained this model. You'll notice first that there's some of these weighting terms. So the first thing, the AI, is we weight the area of each grid cell. I just spoke about how we are living on a sphere and modeling a spherical process. So when I take a sphere and I project it down to a grid, some of you might have realized, for example, when you look at a world map, that Greenland looks huge. If you actually went to Greenland, you'd realize that it's not as big as the map makes it look because it's just at the top of the sphere and has been projected onto the grid to look big. So we want to take that into account. What we do is we take into account the fact that not every square of my grid is equal, and so I'm going to weight that. And then the second thing we weight is the variables. Importantly, some variables are more important than others, so probably you guys here in Qatar care more about the temperature than anything else. And some variables are harder to predict than others. So I can tell you from experience of working on these models, the hardest variable to predict is the temperature 2 meters above the surface of the Earth, which is also the variable people probably care about the most. So in the weighting scheme, we actually upweight certain variables and downweight others. And this is another sort of appreciation of the domain. And the final thing is we weight the sort of elevations inversely proportionally. We care more about things that are closer to the surface of the Earth than are happening way high up in the atmosphere. Cool. Now we've trained our denoiser. How do we actually sample from it? Well, it looks a bit like the following. This is sort of, the parallel to the inference slide that Safa showed. We've got our 2 conditioned inputs, so my sort of 2 frames that I'm going to use to then predict my next one. I'm going to take pure isotropic white noise on the sphere, and I'm going to apply GenCast. Boom. It gets me down to a less noisy state, a less noisy state, a less noisy state, and after a bunch of applications, I've got my residual, which I'm going to add on to the last frame, the current weather, and that gives me my next state. And you might notice that this is where I can do my autoregressive rollout, which we spoke about earlier. I'll just take those 2 again, get my next residual, and again and again and again, until in GenCast's case, we roll all the way out to 15 days with 12-hour time steps. And that's how I've got my 15-day medium-range weather forecast. And some things I want to point out about the sampling. So actually, you asked a great question, and I'll give you an example of something we're doing here that's a bit different to just immediately applying the denoiser. So people like to show this diagram as a way of sort of visualizing what exactly is happening in our sampling process, in the inference, when we sort of go from our pure noise all the way down. And if it looks complicated, really all this is trying to demonstrate is like, we start all the way with our Gaussian white noise, and then that's sort of the trajectory that these states are taking as I'm removing noise from them until I eventually end up at a final state that I want to aim for. So you can think of like the super noisy photo of the dog there, just noise, and then on the right I'll have possible dogs that it could have created. And the idea is that every time I take a step along this trajectory, I'm applying my denoiser, right? I'm removing some noise. And so there's multiple ways you can do that. The simplest way is just follow every step that it tells me to take, a bit like in gradient descent. Or a bit like in gradient descent, I can use some second-order methods. So in GenCast's case, actually at every point we apply our denoiser twice. We say, I'm going to take 1 step, I'm going to take another step, and then I'm going to take the average of those 2 steps. And that's going to give me a better estimate of the direction I want to go to actually end up at my final clean image than if I just took 1 step at a time. And actually, in the end, you'll see that GenCast is quite an expensive model to run. We apply it 20 times, sort of 20 steps, and each time is 2 applications. So you need to denoise GenCast 40 times to get your next state, which is very expensive to run. And it's an open research question in the diffusion community as to how we cut down how expensive it is to denoise using our denoisers. And the second thing is we use a technique called stochastic churn. And what that says is, okay, at every time I'm along this trajectory, when I'm about to call my denoiser to tell me where to go next, I'm going to inject a little bit of noise, which sounds counterintuitive. It's like, hang on, I'm trying to get rid of noise. Why are you adding noise? Well, the reason is I don't want my model to get stuck in like a certain trajectory and only ever give me one possible final reality, one final possible denoised state. I want it to really explore all the possible trajectories it could take to get me down to my final weather forecast. And this is what stochastic churn helps does. It just sort of throws the model a little bit off the path, right? And it makes sure that it actually sort of explores the whole region. So these are 2 techniques that we use in GenCast. Yeah, and as you can see, sort of all it means is that at every stage I'm adding a little bit of noise. Okay, and to be honest, is probably my favorite slide of the presentation. So for those of you that aren't focusing, this is the one slide to focus on. I'm going to compare what a GraphCast and a GenCast forecast looks like for the MENA region, which is quite telling. So what you're looking at here is just sort of a forecast that was made at some point in 2018. And in each case, I'm going to look at what GraphCast and GenCast predicted from 12 hours before, from 5 days before, and from 10 days before. So, I'm expecting the bottom row to look worse than the top ones. The model's probably going to get it a bit more wrong. Okay, so GraphCast. From 12 hours earlier, that looks pretty good. That's pretty similar to what the actual state ended up being 12 hours later. But if I roll this out a bit more, you can see that these states are getting like slightly blurrier and not really matching what the actual weather was. And this is the exact reality of what happens when you train a model to make its best guess. It's going to play it safe. It's like, I don't know, your mom asks you for what's going to happen in 10 days' time. Are you going to get your homework done? You're going to give her a vague answer about, oh, maybe yes, maybe no. That's sort of exactly what's happening here. The model is just blurring. It's saying, I'm going to play it. I'm going to be a bit vague about what's going to happen. Let's look at what GenCast does. Okay, 12 hours before, for those of you that are in the back, you might not realize that this is actually moving around. And each of these images is a trajectory that I've sampled from GenCast. And they all look pretty good. Okay, that's nice. Like the model is pretty confident. All of the future trajectories look kind of the same. And then when I roll it out further, when I look from further back in time, you can see that each of these samples are very different, but they're still sharp. The model is still giving me a realistic future trajectory of the weather, and it's not blurring. And this is exactly how it expresses its uncertainty. It doesn't have to blur anymore. It can just give me sort of trajectories that are further apart from each other, that represent the possible space of what could happen. Okay, so now let's talk about evaluation. Nice. I spent some time at the start explaining to you guys what FID and FVD and inception scores are. And as I said back then, sort of the aim was to make sure that we had realistic and diverse images. But that's not good enough for weather forecasting. If I told you that it was going to be 18 degrees tomorrow at 9 a.m., like that's a pretty realistic forecast, but it doesn't matter if that's not actually what happens. It's not enough to just be realistic. You have to be accurate when it comes to weather forecasting. And so in the paper, in the GenCast paper, if any of you are interested, you'll see that we do a whole range of evaluations. We're really careful about this. But I'm going to break them down into 3 categories, and then I'm going to give you a few examples from each of those categories. Otherwise, we'd be here for, I don't know, the whole day just talking about GenCast. So the first thing we care about is, as I said, skillful. So accuracy. I want to make sure that my model is making good forecasts of the weather in the future. I also want to make sure it's calibrated. What do I mean by that? Well, I don't want my model to be over or under confident. If the model was wrong, I want to be able to see that the model was unsure about the forecast it was making. Going back to this slide, if these turned out to be wrong, then that's fine, because at least it demonstrated that it was uncertain by giving me multiple possible trajectories that the weather could have taken. So that's skillful and calibrated. The second thing I care about is I want my model to capture spatial correlations and dependencies. I want the model to be able to learn this joint distribution, the fact that things interact with each other when it comes to weather forecasting. And the final thing is, as I explained to you, in weather we really care about the tails of our distributions. We care about extreme events, and we want to make sure that the model picks these up. I want to make sure that some of the trajectories that the model is forecasting correspond to these unlikely events happening. So let's break those down. And the final 2, in my opinion, are very nice, concrete, relatable examples. So we'll get onto those in a minute. Okay, so how do we assess skill? In weather forecasting, we use a metric called CRPS, the Continuous Ranked Probability Score. I'm not going to put the equation up on the board, because I myself probably don't even know it. The reality is that sort of the aim is we want to match what we actually observed. If the blue line is the distribution that corresponds to the forecasts in the trajectories that I made, and this dashed line is the actual event that happened, I want to make sure that this blue line is as close to the true observation as possible. The 2 distributions, the CDFs, match. And what we do is we calculate the CRPS for GenCast, so we sort of take an entire year of forecasts. We look at all the trajectories it predicted. In GenCast's case, we always ask it to make 50 guesses, and we compare that to what was actually observed. And then we're also going to do it for a baseline model called ENS. And this is was the SOTA model before GenCast came out, that was the sort of a physical baseline that had existed for a number of years. Okay, so we compute the CRPS for both, and we get the following. And in the weather community, we call this a scorecard. I think the reason we like to use it is just because it looks very pretty. but it's also actually very convenient to just glance at and get an appreciation of what's going on. What you're looking at here is everywhere this scorecard is blue, GenCast has a better CRPS than ENS, so it would have made a more accurate forecast. And luckily there's a lot of blue, otherwise I probably wouldn't be stood here talking to you about GenCast. Every single sort of column, so the x-axis is how far into the future the prediction was. Every single row is how high above the surface of the Earth the prediction was. And then each of these boxes is a variable. So you've got like temperature, wind, sea level pressure, and so on. And yeah, and the color bar represents just how much better. So we've got, so number one, done. We've got a better CRPS than the baseline. The second is this calibration. And for this, we use a metric called spread over skill. So remember, I said the idea is the more wrong my forecast was, the more uncertainty they should have had. And the way I'm going to measure this is by taking the ratio of the variance in my ensemble members to their actual error. So if you think about this for a moment, if the variance was high, but the error was low, then my model was underconfident. It wasn't certain in what it was saying, even though it got it right. And I'm going to get a big number here. If the variance was small, but the error was big, I'm going to get a small number. This is just your basic fractions. But that means that the model was overconfident. You know, it was like, no, I'm telling you, this is exactly what's going to happen. And then it got it wrong, and it shouldn't have done that. So in an ideal world, I want these two numbers to be the same. I want to get a fraction that equals 1. And so we plot exactly this. We look, as a function of time, what was the spread over skill at each of these times? And in an ideal world, our lines would be perfectly flat. The model was never under or overconfident. It was perfectly confident. It was perfectly calibrated. And you can see that GenCast's lines are flatter than ENS's lines. So we've done a better job of calibrating our model. Okay, final few slides. And for me, these are my favorite evaluations because they're relatable. For spatial dependencies, we looked at the task of wind power generation. And so explicitly what we did was we sort of took a map of the Earth and collected about 6,000 wind farm locations. And we wanted to see how well the models could do at predicting the output of these wind farms. But remember, I said spatial correlations. So first what we did was we pooled the Earth. We divided all these circular regions around the Earth. And we said, okay, I'm going to collect every single wind farm that exists in each of these pooling regions. And then I'm going to ask the model to predict what the sum of the power generation from all these wind farms was. And that's exactly how I'm capturing a spatial dependency. I'm asking it for the sum in a space, not just a single wind farm at a location. And you can look at the following. This is a plot comparing the CRPS of how GenCast did at this task versus ENS. It's a relative plot, so it's just sort of the difference between it. And we can see that sort of at the shortest lead times, we're beating ENS by about 20% on how well we're forecasting this summed wind power output. Cool. And then the final evaluation, as I said, predicting extremes. And for this, we look at cyclone forecasting. So hurricanes, cyclones, typhoons, which are all sort of a similar event. Here's a really nice animation. I mean, nice in the animation, but it's a sad event of GenCast forecasting Typhoon Hagibis that happened in 2019. What you're looking at is the red line is actually where the typhoon went, and the blue lines are where the samples that we drew from GenCast said that the typhoon was going to go. You can see it, I mean, it gets it pretty right. You know, it's quite close. And this is at 5 days before the actual landfall. So 5 days in advance, we said where the typhoon was going to go correctly. And for that, one of the metrics amongst many that we use is the ensemble mean, the error of the ensemble's error track. And simply all that is I sort of going back here, I'm going to calculate the mean track that these ensembles are forecasting. I'm going to look at the distance between that and what the actual path that the typhoon took, and I'm going to calculate what the error was. And you can see that again, GenCast has a better error of ensemble mean track than ENS does. Awesome. So to point out, this is, you know, I'm but one of many, many people on this amazing team, so I really want to give credit to them. We recently released our paper in Nature in December, so if you want to scan the QR code, and all of our code is open source as well, so feel free to play around and ask questions on the GitHub repo. Thank you. Do we have time, or? Oh, go for it. Here. Wait, do you want to wait for the microphone?
Thank you for the presentation. I just had a question related to how do you make sure that model do not make hallucinations, like because you're unrolling through time, based on previous steps. And in video generation, we sometimes see unrealistic frames, like a horse flying or something like that. I saw you have some metrics like empirical CDF compared to real CDF, things like that. But from what I see from a mathematical perspective, there is nothing like that prevents model to hallucinate, except that you condition on previous two steps.
Yeah, I mean, this is a great question. So actually, first of all, I'm gonna point something out which makes this like even more surprising that the model does so well. You'll notice that like when I spoke about video diffusion, I mentioned that they sort of, sorry, I'm just gonna go back to this sampling slide. I mentioned that in video diffusion, they add this extra frame dimension and they sort of have temporal attention across that. In GenCast's case, we're actually kind of cheating. We're going in between. At no point in the training has GenCast got a notion of the fact that it's like rolling out within a video. We only ever get it to predict the next frame conditioned on the two inputs, and then we just auto-regressively stitch this together at inference time. So actually, I'm kind of agreeing with you that it's pretty surprising that this works well, considering that like it doesn't even know that it's part of a trajectory per se. It just knows it's making one step. I mean, in some sense, the answer to your question is like, in the same, for video diffusion models, you train them as well as you can, and you evaluate to make sure that they're not hallucinating. And we've done a lot of evaluations to make sure that the model is creating realistic settings of the weather that are also accurate. A lot of people in the weather domain would like us to take this further, and they say things like, you should be imposing physical constraints in your model. Like you should have things that say, for example, that precipitation can never be negative, or that certain laws of fluid mechanics should be obeyed. And the reality is there is a bit of a trade-off between whether or not you think that deep learning should be given priors in the model, or whether you should just let it learn from the data. So the direct answer to your question is that like the way we've made sure it's not hallucinated per se is to check in evaluations that what it is creating is accurate, calibrated, and realistic.
A quick question, how expensive is it to get one trajectory?
So I guess we run our model on the TPU v5s, which I think are equivalent to H100 GPUs. And on a single H100 GPU, we can roll out our 15-day forecast in 8 minutes. To give you a reference, the chorus ENS, which is the corresponding SOTA baseline that I mentioned, takes a few hours to produce its forecast.
Okay, thank you.
I have a question.
Sure.
So in the sampling, you mentioned about the second order solver. I want to know, like, if we increase the, like, if we use a higher order solver, will it improve the performance?
Yeah, I think at that point, it's a bit of a trade-off, right? It's like same with higher order descent methods. You're trading off the cost of like choosing the trajectory to follow with then how many of the steps you can take. And I think at that point, the question is, do I want to spend 20 iterations of second order steps, or would I rather spend 40 single iterations or 10 subsequent steps? And I think sort of most people in the literature usually settle on these second order solvers in diffusion's case. There's a great paper called Elucidating the Space of Diffusion Models. It's by a group from NVIDIA, and they really deep dive into sort of these trade-offs that you can make in diffusion models, if you're interested in checking that out and seeing sort of the reasons why you might go for one or the other.
No, thank you.
Hi. My question is more from, yeah. So my question is more from the scientific perspective. I do similar stuff, but for solar forecasting.
Sure.
I don't come with a background in CS. I'm a mechanical engineer. So one thing we like from these models is to understand the interpretability, like what's actually happening under the hood of these networks. The second thing is, have you looked at like a way where it's a hybrid version between the current state of the art, which uses more physics relative to this pure data-based prediction, and can we come up with like neural networks that are physics informed and something like that sort of hybrid approach?
Yeah. Before I answer, Safa, do you want to also come in case anyone has questions for you? Yeah, so to answer your first question about interpretability, our team per se hasn't done much work on that. There have been papers out there where I guess one form of interpretability is to look at what happens when you perturb like the inputs to the model and see how the model reacts to that. So there's a great paper out of a professor called Greg Hakeem at the University of Washington, where they basically took these machine learning weather models and they said, okay, if I make this like really bizarre input state, how does the model react to that? We know how it should react from our physics laws. Does it also follow those? And I think they found that generally it did. On the other hand, we know that these models have problems where they underestimate like the intensity of wind in hurricanes, for example. And so I think there's still some room to be made in interpretability of like, why is that happening? Where is this coming from? And then I think your second question was about hybrid approaches. We haven't, but there's actually a team at Google Research called Neural GCM, which have done exactly that. They sort of, their model has two parts to it. This like physical core, which is your standard sort of physics equations that they solve forwards in time, and then an MLP, a deep MLP, that is correcting the outputs of this physical core. And I think this is a general trade-off in machine learning, right? It's like, do you go for a hybrid approach? Do you go for a pure deep learning approach? And I think we've gone for the pure one, they've gone for a hybrid one. Some of their benefits are that they get much more stable, long rollouts. So they can do climate forecasting out to years into the future because this physical core is grounding them in realism. If there's any questions for Safa?
Yeah, one question for you.
Who,
yeah,
Safa?
No, for you.
Oh, does anyone have a question for Safa? There. Okay, then.
I can start. Thank you for the great talk. And is there still a future for the diffusion models compared to LLMs? So that's the first question. And then the other two questions, like one for, you mentioned the Frechet inception distance. What is the difference between the Frechet inception distance and the Frechet distance? And the second one, also you have mentioned extreme events. So do you employ special tools for that, like extreme value theory or some detection based on the uncertainty, or it's like detected with the diffusion model? Thanks.
There are still many open challenges. For example, one of them is sampling. So as Andrew mentioned, sampling is very slow currently. So there is a lot of research looking into ways to speed up the sampling. Also, we're optimizing an elbow, right? So there is a new direction called flow matching. They're trying to derive a closed form expression of the log likelihood. And they use some tricks to basically train a flow model to have an exact log likelihood. But then there are some drawbacks there too. So it's a very active research area. I think there is a lot that still can be done. And these are two examples.
And then I'll quickly answer your point. So about the Frechet distance and the inception distance, the Frechet distance refers to like it's a metric of computing the distance between two distributions. And then the inception distance is just with specific reference to the way that it's like specific reference to the metric that is used to compute the distance between the two distributions of the features when you're doing image generation. So this FID was introduced in a paper on GANs, I think back in 2017, and that's what they named it at the time, to say we're using this distance metric and we're doing it for this task of verifying how good images are. And then I think about your extreme value, if I remember correctly, so I think we have a metric in our paper called like a relative economic value, which I think might be similar to what you just referenced at the end with your extreme value theorem. I'm not so sure, but that might be relevant. Sort of what we're looking at there is like, how expensive would it be to either prepare or not prepare for an extreme event based on how the probability that the model gave to this event occurring. And I'm happy to talk about it offline afterwards if you'd prefer.
Yeah, thank you, Safa and Andrew, for this amazing talk. I have a follow-up question on extreme events. So one of the most important things to evaluate for is extreme events and the prediction of extreme events. But my question is extreme events, usually there is a scarcity of data for extreme events because they are extreme and they rarely happen. What happened, like what special care is taken during training to make sure that we are able to predict extreme events? Or is it just a black box that, wow, we're having a good prediction of extreme events?
Yeah, I think you probably don't want to fall into the trap of like overly training your data on a subset of your data set. So we're not per se treating these extreme events any differently during training. In our training, we're just sampling random frames within our Era 5 data set, which is a data set of about 40 years of data. And this will include extreme events. I mean, over the course of 40 years, a number of things that have happened. I think also, unfortunately, with things like climate change and global warming, more things are happening. So it's definitely showing up. And actually, to relate to that, we noticed that these models do particularly better when they're fine-tuned and retrained on more recent data. And I think one of the realities of that is that the distribution of the weather on the Earth is now changing. We're seeing more extreme events, and there's more of these present in the data set that we're training it on. But yeah, I mean, other than that, really, it's an open question. A lot of people are wondering, like, will these models generalize to things that are out of the distribution of the data that they saw in their training? And I think that this is what we've tried to show in our paper. You know, all the evaluations are done on what we call a causal split, so it's a held out set. We trained it up to the end of 2018 and did all the evaluations on 2019. So these are events it's never seen. I mean, Typhoon Hagibis was something it never saw during training, and it got that pretty right. So I think it's the best you can do is evaluate, and then I guess do some interpretability, which we haven't moved on to yet.
Okay.
Yeah. Sorry, I'm going to let you choose.
Hello. I first want to thank you for this presentation. And as a namely weatherman, I am really interested on this thematic. So I divide my question to 3 parts. The first one is the generalizability, what we call the transfer learning. Since we are motivated as weather forecaster to apply GenCast or GraphCast in high resolution domains. So we find always this difficulty of that we need to retrain the model instead of using a pre-trained version of GraphCast. And also another motivation to this is that we are going to go to era 6 now, reanalysis, which have 9 kilometer resolution instead of 31 kilometer resolution. So are we always have this obligation to retrain the model again and again?
So let me start by answering that before you ask the other two. I think this is probably, I mean, like, there's like the actual, you know, practicality of what you have. If you have your model that is like taking in data of some resolution, you can't just randomly feed it in data of another resolution without adapting something about your architecture to do that. And I think the reality is that once you adapt it, you probably need to do some fine tuning so that your model is able to take this into account. But it's I mean, like, a lot of people like to think about stuff like this with this whole foundation model rhetoric around, like, oh, let's just take a model and train it on loads of data from some sort of domain and then use it to sort of fine tune at the very end to get specific downstream tasks. And you could think of it like that. I mean, like, there's no reason why you can't take a model like GenCast that's been pre-trained on Era 5 and then fine-tune it on specific higher resolution data. And actually, the way GenCast was trained, I missed out a detail in the talk for the purpose of time, is we actually pre-trained GenCast at a coarser resolution. So a resolution of the Earth that was about 120 by 120 kilometers, what we call 1 degree resolution. And then it's only at the end of training that we fine-tune it up to this coarse, this finer 30 by 30 kilometer resolution, which GenCast sort of forecasts that. So these are, I think in that sense, it is somewhat transferable. Yeah, I mean, but as in, like, this whole just like plug in a different data set to a model that was trained on something else, I don't think that's just a weather thing. It's a general blocker you're going to have.
Yeah, my second question is about the quality of the data in input. Since we know as weather forecasters that the Era 5 data is not that for a good quality, especially in the regions when we have less observations, since the area analysis. So we're talking about the southern hemisphere and regions like that, Pacific and so on. So was there any pre-processing that have been made before to, let's say, enhance or make this balance between the regions when we have low quality of data and less quality?
So for those of you that aren't very familiar with weather, I'm actually just going to bring up the slide which is being, like, sort of the idea that's being referred to. Oops, sorry. A lot of slides back. Okay. I spoke about in this slide the process of how we make our weather data, right? And we're taking loads of these, what we call sparse observations. You've got like a satellite over here, a weather station over there, and I'm asking to create a state that represents the whole Earth. I think you can imagine that there's a bit of a problem there, which is that, like, if I don't have a satellite or a weather station in a location, how am I going to get a measurement for what the weather was actually like over that location? And basically what this process ends up doing is a bunch of interpolation and extrapolation, and that's how I get an approximation of what's happening there. So the problem which sorry, what's your name?
Badruddin.
That is being referred to is that, like, this is an erroneous procedure. No, we didn't do any pre-processing, but this is what we're moving towards. The idea is, let's move towards using more data sources that aren't just in Era 5. Let's collect as many of these satellites as possible, there's a lot of teams at Google, for example, that do research on installing more weather stations in the southern hemisphere, and let's directly use these observations as opposed to just relying on this like imperfect approximation and extrapolation.
Okay, so I have a last question, but
I might
it's time for
for Safa. Oh, okay,
Safa. When you have talked about diffusion models, you are talking mainly about all these Gaussian distributions. So what if our, for example, parameter is following an extreme, let's say, distribution, like, for example, Gumbel for floods, or, for example, Poisson? How can we treat this kind of sample this kind of distribution using diffusion?
I mean, like, first it has to be easy to sample from, right? And then if you pick something complex, then you have to justify why did you pick that? Like, what's in the data that made you believe that your distribution should follow that complex form as opposed to something as simple as a Gaussian? So I would understand it if you actually choose a multi-model distribution, because you might believe that there are multiple modes. But something like Poisson or something else with some underlying assumptions, I mean, it might be, not the most trivial and obvious choice to make, given that we're just trying to denoise something we don't really understand.
Okay, and we can we, however, approximate this, let's say, this complicated laws with the Gaussians and diffusion models?
You're applying to. It seems like you're doing this already, right? So it seems like Gaussian is good enough. And if you apply many of them, then it seems to be doing a good job. And you're actually, I think the magic is in the noise, because like you basically, if you sample different samples from this noise distribution, the model would learn to map these different samples into different modes automatically. So it's doing well.
Okay, thank you.
Just up here. Hi. I have a question. So again, sorry on GenCast. So last year in Doha, we had a really bad tropical thunderstorm here, and a lot of people are saying a big cause of it is the cloud seeding that happens in this region. How does GenCast deal with kind of artificial weather patterns like that?
Yeah, so I think probably first, if we're talking about the same event, I'm pretty certain it had nothing to do with cloud seeding. I just want to correct, I think that was a bit of misinformation that was going around at the time. I think the event was, actually I remember at the time going back and looking at our forecast, and we picked up the presence of the storm like 6 days in advance.
Nice.
And that's not something which, like the scale that cloud seeding occurs on is like under a day, right? And then in terms of those events, yeah, we don't really account for those. Also, the reality is something like cloud seeding is a lot more local than the resolution that our model picks up. I think cloud seeding happens, on like a city scale. At the end of the day, what you're literally doing is like seeding your clouds with some compound that makes molecules of water bind to it and then fall and rain. And sorry, if anyone knows about cloud seeding, apologies if that's incorrect. That's my understanding of how it works. And so I think that phenomenon is just too local for our model to pick up anyways, per se. But I'm pretty sure the floods had nothing to do with cloud seeding. So,
okay. Cool, thank you.
No worries.
So, okay, question for Safa. So, why do diffusion models not suffer the same like mode collapse things like GANs do? What's the intuition?
So they're essentially following the score function. And if you learn the score function, then and basically the score function is the score function of the noisy data. So at every point in the space, you will be directed to the closest mode. Hence, it's unlikely that at different points of the space, you will have all the vectors pointing to the same mode. So yeah, this noise actually term is proportional to the score of the noisy data. So if you are closer to mode A, then you will learn to get to mode A. Next time you sample, you're closer to mode B, you'll learn the score at that mode for mode B. And then eventually, wherever you land, you will learn to get to the closest mode. Yeah.
So just a quick question for you. Is there a way you could distill GenCast into GraphCast, or?
So to be clear, what do you mean by distill there? As in, like, what is it about GraphCast? What would a distilled GraphCast look like?
GenCast has a broader, it has more uncertainty in it. You were saying GraphCast is more deterministic. Maybe it's more efficient model in also.
So there's definitely ideas around like distillation of diffusion models. And I think it's something we've thought about before, but I think, remember, there's still like a distinction to be made here, which is I'd still need a way of drawing different samples from my distilled GraphCast, if that's the phrase we want to use. And so I just need to make sure that whatever distillation technique I use, which to be fair are quite successful for diffusion models, really still captures this calibration. To give you an example, like in the GenCast paper, we actually provide as a baseline GraphCast, which has just had its inputs perturbed with some Gaussian noise. And we see that it's an okay model, but that its forecasts are really overconfident and are not very accurate. So like the name of the game is still being able to draw good samples from whatever model you've distilled into. I think this is the last question. So who hasn't asked a question? Go for it.
It's not a question, just a thing to Sanjay. So GraphCast is GNN-based. With graph neural networks, it's much harder to utilize your flops count as much. So distillation wouldn't get you as much. With diffusion models, you very much dense computation forward and backward, and you can plug in a lot more compute in parallel as well. So you wouldn't benefit as much from distilling into a graph model.
You need to ask yourself the question of like, what am I trying to aim for by distilling my model? What benefits is it going to give me? And the reality is something like GraphCast, probably not much because the GNN is not efficient.
Yeah. If you want to distill, probably diffusion and transform will make more sense.
Exactly.
Sorry.
But the question of diffusion is of distillation is still a very valid one. Just maybe not into GraphCast. Cool. I think that's it. Oh, do you want maybe last question here? And then I'm here for the rest of the week, and I think so is Safa, so please come up to us at any point and ask more questions. Actually, that's better, then you can't embarrass me here.
Okay, so it's to you, Andrew.
Uh-oh.
Yes, it's about the Markov assumption.
Yes.
I understand the motivation behind it physical laws are memoryless, etc. But that's only true if we know the full state of the system. And I think there has been like classical results since the 50s. There was this British scientist called Hurst. He studied discharge in the Nile River, and he found that it has a long-term memory, actually. So my question is, have you tried conditioning even in
so I think the reality with deep learning is you make these assumptions and then you go, let me just sort of still empirically test them out to see, right?
Yeah.
And this is really, first of all, the idea about this basically having a partial observation of your system is exactly the main motivation behind why we relax it to a second order Markov assumption as opposed to the standard Markov. But the empirical answer is we tried. We tried conditioning it on 3 frames and 4 frames and 5, and it just plateaus off. It doesn't get any better, and now you're just making your life harder by conditioning on something that isn't helping you out. That's a great question. But really, that's the partial observation is why, I guess, is an explanation retroactively for why we relax to a second order assumption.